Hello again, hackers. Today our target looks harmless, an echo server. We type text, it gives text back. But beneath that echo is a stack frame, a missing size limit, and one tiny return instruction that lets us borrow code from libc. This is libc, not shellcode, not guest addresses, but a traced route through code the process already loaded. We start with exactly what the challenge gave us. No friendly C source, no comment that explains the bug. Just a binary, a libc, and a makefile fragment. The raw ls output stays on screen first. Then file tells us that vom is a 64-bit dynamically linked executable and it is not stripped. The supplied libc is a strict 64-bit shared object. That is our evidence workspace. And every clean teaching fragment in this episode will visibly descend from it. The makefile is build context, not source. It says 64-bit, no PIE, and the local run path. The binary still gets the final word. RateElf says its type is EXESC, GATXC, true RST-SCAC is readable and writable, but not executable. The dynamic section gives us runpath dot slash and new row, while the symbol check finds no stack canary symbol. Together, those rows mean no PIE, next enabled, no canary, and partial row. Next changes the attack shape. Bytes can sit on the stack, but they cannot become instructions, so our stack must become a root made from addresses. The symbol table is our map. Because this binary is not stripped, it names convert core tower xace at 0x467, do unsec stuff at 0x468, and main at 0x468, and main at 0x473. Scan, conversion loop, and put. It is only a provisional map until the disassembly proves it. Notice the discipline here. The friendly diagram is pulled out of the complete symbol table, not invented on an empty canvas. Now we open all of do stuff for isolating the bug. The function creates a stack frame with sub RSP 0x90. It calculates RBC minus 0x80, then passes that address to scanf. A second scanf lands at RBC minus 0x81. The loop begins at 0x407 calls convert, case, then the function calls puts, leaves, and returns. The format strings are not friendly source text, they are raw bytes in raw data. The dump says 2555E0A5D00% open bracket caret. New line, close bracket 0. That decodes 2% bracket caret new line brackets, scan until new line with no width limit. The next bytes decode to %C. The first scanf is the hazard. And its proof is the router DOM, joined back to the call site. The input begins at RBC minus 0x8 EC. That places the saved base pointer 128 bytes above the buffer and the saved return address 8 bytes after that. 128 plus 8 gives us the control offset 128 plus 8. but this challenge has a strange, visible side effect. Do stuff sends the first 100 bytes through convert stuff car cast. The disassembly checks letter ranges, then adds or subtracts 0 by 20. The loop bound compares the counter with 0 by 63, so indices 0 through 99 mutate. A wall of ahs can echo as ah 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 ah. Our return address begins at byte 136 safely after that mutation zone. The counter itself sits at RBP-0 base 8 inside the overwritten region. When the loop finishes, it leaves 0 base 64 there. ASCII lowercase d. So a trailing d is an echo artifact, not the leak. The leak is the next thing we would deliberately route to std out. To defeat SLR, we need one real libc address from this run. The relocation table says puts uses a jump slot at 0x61018. The PLT says puts at 0x454 jumps through that got entry. So puts at PLT can print the pointer stored inputs at GOT. On x86 Obicumber, the first argument is RDI. The key symbol table does not give us pop RDI read, but the byte stream inside libc init does. In normal decoding, we see 41.5 of C3 pop FET ret. Start 1 byte later at 0x400 913 and 5 of C3 becomes pop FD ret. That shifted decode is not a guess, it is a real disassembly command. Finally, init gives us a plain ret at 0x450u. It looks boring now. Later it will be the alignment scheme that lets the second chain survive libc. Stage 1 now has a provenance trail for every block. 136 bytes of padding come from the stack frame. The shifted decode gives pop RD ret. The relocation table gives puts at GOT. The PLT gives puts at PLT. And the symbol table gives do stuff again. The chain sets RDI to puts at God, returns into puts at PLT, and re-enters do arg stuff. On a matching runtime, puts would emit ugly raw pointer bytes. We do not have that runtime here. The actual local launch fails before the program begins. The supplied libc and the host loader disagree at early initialization. That is not a shell, not a leak, and not a reason to fake one. It is a concrete runtime constraint. Saved as evidence. The supplied lib still gives us its internal distances. Return finds puts at offset 0x8a, the seer, and system at 0x4e0. Strings find /bin/it 0x1b forte. SLR can slide the entire library, but it does not change those distances. With a real stage 1 leak, libj base equals leak, puts minus 0 base 8a find thou, then system is base plus 0 base 4 base 0, and /bin/a space plus 0 base 1 base find thou. One known address would align the whole library ruler. In this render, those runtime values remain symbolic because the required matching run is unavailable. Stage 2 is the borrowed function call, overflow again with 136 bytes. Use the ret shim at 0 base 452 to shift the stack by one address width. Then publish the runtime address of /bin/n to RDI. The final saved return address is runtime system. In compact form, the stack route becomes ratshim, publish ratshim system. The added threads is not decorative. Some lived paths expect stack alignment. The shim consumes 8 bytes and changes the alignment before the root enters libc. We can teach that mechanism from the real gadget and ABI model. But we do not claim a local shell without a matching loader. Here is the honesty gate. A final exploit transcript must come from the real remote service or local runtime with a matching LD Linux loader. This workspace contains neither. The captured local result is an ld.so inconsistency assertion during early initialization. That is where this proof stops. The analysis does not disappear. Challenge files led to build context. Reader proved protections. Symbols named door, stuff. Disassembly found the stack frame. Raw data exposed the unbounded scan. The relocation table named puts at got. The PLT named puts at PLT, shifted bytes revealed, obey direct, and the provided LEP6 supplied the offsets. The missing item is only the runtime transcript, and it remains visibly pending. The challenge-specific pitfalls are worth keeping. First, out comes from converts there's case and a loop bound of 0x63. Only the first 100 bytes mutate, while a rope chain at 136 survives. Second, the trailing D comes from the loop counter at RBC-0xC18 ending at 0x64. It is visible, but it is not the leak. Third, the pop RD ret gadget begins in the middle of 41 5EC3. So the address is 0x400913, not the address of the full pop R15 instruction. Fourth, a provided libc is not a usable local runtime unless its loader matches. The broader ret2 libc lesson is evidence flow. Find the overflow. Measure control. Find a way to set the first argument. Leak one known libc function. Subtract its offset. Add the targets. Then return into code the process already trusts. Today the stack never became executable. The payload never became code. It became a path. One route to leak runtime, one route to call system. That is read to libc, not a spell, a traced route through the binary's own machinery.